So we've looked at the three types of decay. Alpha decay, which produces a alpha particle, which is a helium nucleus. It's deflected as a positive particle in a magnetic field. Its penetrating power is not as great as beta, which is deflected as a negative particle, although in this video we're also going to look at something called beta positive decay. And then finally, the type of radiation with the greatest penetrating power is gamma decay, which is a form of EMR. But in this video, we're going to focus on alpha decay and beta positive, beta negative decay, and how to show that with something called isotope notation. Now, here's an example of alpha decay. We have a uranium-238 nucleus, and it decays, and in that process it emits an alpha particle here, that helium nucleus, and a thorium nucleus as well. Now, one thing you'll notice is the notation that's used here. Now, this is uranium-238. Sometimes it'll just be communicated this way, uranium-238. This is thorium-234. And then this is helium-4. Now, a couple things with this notation. That top number is what's called the mass number, and it's the total number of nucleons, the total number of protons and neutrons that are present in that nucleus. Now, that number can vary depending on the isotope that is present. With different isotopes, we can have different number of neutrons. So we might have uranium, other forms like 239 or 240, but the thing that won't change is the actual number of protons. That's this number on the bottom. So helium has 2 protons, uranium has 92 protons, thorium has 90. We can get those values from our periodic table. So whenever we're dealing with, so let me clear that, whenever we're dealing with isotope notation, so the one example we had was uranium-238. This number at the top is the mass number, the total number of nucleons. This number at the bottom gives us the number of protons. Now, if at any point we want to find out the number of neutrons, all we have to do is take this top number, this mass number, subtract the number of protons, and then what's left is the number of neutrons. But the number of protons you can find on your periodic table. This is in your data booklet. For any element, it'll tell you the number of protons, and that's the identity of the element. It's not going to change with whatever element that we have present. So let's look a little bit more at this alpha decay. One thing you'll notice as well is a very important physics principle is at play here. And just like a lot of the other physics principles, this is based on conservation. And in this situation, when we're talking about decays, we need to keep in mind the conservation of nucleons. So the total number of nucleons, again that's the protons and neutrons, must remain the same before and after a nuclear decay reaction. So we can write out this decay event in isotope notation, and we'll look like this. We have uranium-238 with 92 protons undergoing an alpha decay. So in an alpha decay, we produce an alpha particle, which is that helium nucleus. Now, in order to find out what the other daughter nucleus will be, we don't need to know necessarily that it's thorium. We can use this physics principle of conservation of nucleons to determine the mass number. This needs to be 234, because if I had 238 nucleons before, I need to have 234 nucleons after. And if I've emitted 2 protons from that daughter nucleus, then now I have 90 left in this actual, in this alpha decay. Now to find out what element that will be, if I didn't know it was thorium, I can look on my periodic table. The element with 90 protons is thorium. This is an alpha decay using that isotope notation. So here's another example, an iridium 168 isotope. So it's iridium 168 going through an alpha decay. So again, I need to know the number of protons for iridium. I look at my periodic table. Iridium is 77 protons. Now if it's an alpha decay, I know that it's going to emit an alpha particle from that nucleus. So that's helium. There's my alpha particle. Now another way you might see this written is like that. So that's another way to communicate that same information. You can see it as that, or you may see it as helium. They're both different ways of communicating an alpha particle. Now, again, using conservation of nucleons, I'm going to have 164 nucleons and 75 protons. 75 protons is rhenium. Now, possibly rhenium could also undergo another alpha decay. Sometimes these can happen in sequences. If that does happen, again, I'm going to produce an alpha particle here. And I keep going down. So now I'm going to have 160 as my mass number, 73 protons, and 73 protons is TA. So I can use conservation of nucleons to actually determine the mass number, determine the number of protons present, as long as I know that it's an alpha decay. Now, we're also going to look at something called beta decay. We've talked about beta decay already, but there's two types. There's beta negative and beta positive. Beta negative decay produces a negative particle that's deflected in a magnetic field. And there's this other type that we haven't really talked about yet, but beta positive, which produces a positive particle as deflected in a magnetic field. Now, beta negative decay happens during a process that at first seems crazy. It's kind of a neutron falling apart and becomes a proton and electron. Now, you'll notice that conservation of nucleons is still consistent here. I have 14 nucleons at the start, and I have 14 nucleons after this beta negative decay. So it doesn't violate that conservation law. But what you'll notice is that previously I had 8 neutrons, and now at the end I have 7 neutrons once it undergoes that beta negative decay. We're going to zoom in on the protons and neutrons and what actually makes those up in a later video, and it will make more sense when we look at beta negative and beta positive decay then. But for the purpose right now, it's a neutron giving us a proton and a negative beta particle. Now, one thing you'll notice here is that there's an electron being emitted, and electrons are very small. Now, using other conservation laws like conservation of momentum and energy, that electron should be going very, very fast. Now, in beta negative decays, those electrons actually aren't traveling as fast as expected. And so that caused scientists to actually determine that there must be another particle that also has some momentum coming off. And that's this antineutrino. An antineutrino is an antiparticle to a neutrino, which you'll see at the bottom in that beta positive decay. But that antineutrino is important for conservation of momentum and energy because those electrons move very small. So the big idea here is in that beta negative decay, I produce a beta negative particle, which is an electron, but it's 0 nucleons, an antineutrino, and my new daughter nucleus. In beta positive, I produce a positive beta particle. So in this situation, I have a proton, and then at the end, I have an extra neutron. And in that process, I produce a positive beta particle, which is called a positron. It's an antiparticle to an electron. It has the same mass, it just has a different charge. And when we look at particle tracks in later videos, we'll look at more evidence for these positrons. Now, same reason why we need the antineutrino. The neutrino is the particle that goes with the positron in a beta positive decay. And again, it's important for conservation of momentum and conservation of energy. So we can look at this situation. We have potassium 40. So potassium 40, and the number of protons in potassium is 19. It's known to go through beta positive and beta negative decays. We're going to write out the decay equation for both types of beta decay. So the first one we're going to look at is beta negative decay. And this is where we have a negative beta particle. Now, again, in beta negative decay, I need to remember that I need an antineutrino. Antiparticles just have lines over top. So I need that antineutrino for conservation of energy, conservation of momentum. When I look at my daughter nucleus that's formed, again, conservation of nucleons tells me that I need 40 nucleons here at the end. And in beta positive now, I need 20 protons at the end. Now again, my nucleons are still conserved. I have this negative particle here, so charge is conserved as well. And then I can find out what that actual element will be on my periodic table. Element 20 is calcium. So that's beta negative. Now, if potassium were to undergo a beta positive decay, so I produce a positive beta particle, a positron. Now, again, conservation of momentum, conservation of energy requires me to include a neutrino. Then using conservation of nucleons, my mass number is still 40. And now in this situation, I have 18, because my charge needs to be conserved as well. So I have 18 protons. So my charge is also conserved. And then I can look at my periodic table. 18 is argon. So again, in beta negative decay, I have a neutron that is giving rise to a proton and electron. And then in the other situation, I have a proton and electron forming beta positive decay as well as a neutron, extra neutron. So that's beta positive, beta negative decay. Now, one other type of radiation that we've talked about is gamma radiation. You'll notice in gamma radiation, this is an example of it, that the number of nucleons doesn't change. Gamma radiation is very common after beta positive and beta negative decays. Sometimes the nucleus, after it undergoes those decays, will have a lot of extra rotational energy, different types of energy. And in order to reach a more stable form, it will give off a gamma burst. Now again, gamma is a form of EMR, it's a form of energy, but it doesn't affect the number of nucleons present in that element. So you'll see that the number of nucleons doesn't change, the number of protons doesn't change. All that happens is that I emit this gamma photon, or I emit some gamma energy, and that helps that nucleus reach more stability. So the three types that we've looked at in this video are alpha particles, where I can use conservation of nucleons to actually determine the daughter nucleus that's formed. There's beta negative and also beta positive decay. So two types. So I can produce an electron or I can produce a positron. So beta negative particle, I can have beta negative decay or beta positive decay. Now this follows conservation of nucleons and also conservation of charge to determine what my daughter nucleus is going to be. And then in gamma decay, I just emit a gamma burst in order to reach stability in the nucleus.